Okay, so 6.5 notes is the behavior of the accumulation function. So remember yesterday when we talked about the accumulation functions, we say that they're in the form capital F of x is equal to the integral from a to x, f of t dt, where a is a constant. And then we also are recognizing that the derivative of capital F of x is equal to f of x. So in this notes, we are going back to Unit 5, and we are looking at the comparison between the derivative of capital F of x and then the function. Okay, so for each of the following. So first it says capital F of x is increasing when the derivative of capital F of x is greater than 0. Or we can say when f of x is greater than 0, okay, since its derivative is equal to f. Okay, decreasing is the opposite. So the derivative of capital F of x is less than 0, or we can say that the function is less than 0. Okay. Relative max and relative min is when we are changing signs. So we have the derivative of capital F of x for relative maximum changes from positive to negative. And this is going to be the same, but with f of x. Okay, so f of x is also changing from positive to negative for the relative maximum. Okay. Relative minimum is going to be the opposite. Okay, so we're changing from negative to positive. And again, this is the same for f of x. Okay. Then we have concavity, and remember concavity is when we looked at the second derivative. So this is going to be the second derivative of capital F of x. When it is greater than 0, we know it's concave up. And that's the same as us saying that the derivative of f of x is greater than 0. Also tells us concave up. Okay. Opposite for concave down. It's going to be less than 0. Okay. And then a point of inflection is going to be when that second derivative changes signs. And of course, that is going to be equivalent to the first derivative of the original function changing signs as well. So again, this is making the connection between the accumulation function and then the original function f of x. Any questions so far? Yes?
Is it f prime or f prime? Like, sorry.
For what?
Concave up and concave down.
For concave up, it's the double prime of capital F of x. And it is just prime of f of x because the derivative of capital F of x is equal to the function. So if we take the second derivative, it's just equal to the function's first derivative.
And then same for point of inflection, just f prime.
Correct. Correct. Okay. So example 1 gives us g of x is equal to the integral of a to x f of t dt, where the graph of f is shown below and a is a constant. Okay. We know that if we were to take the derivative of g, okay, that would give us f of x, because if we take the derivative of an integral, cancels out, and then we're just left with the function as t, with t as a placeholder, and then we take that upper bound of x and plug it in. So we have the derivative of g of x is just equal to f of x. Okay. For these type of questions, they're going to have you answer each of the following. So these ones have multiple parts. So using the equation and the graph, we're going to answer the following. It says find the following x values. So A says the relative minimum of g. So the relative minimum of g. We know relative minimum is when the function changes signs from negative to positive. So what x value would that be on the graph?
3.
So the 3 is going to be the opposite. That's going to be the relative maximum. Okay. Good. Right here. Right here. Somewhere in there. We don't know if it's 5.5, 5.4, 5.3. We're going to put something along those lines. So x is approximately 5.4. As long as it's in that range, it's fine. Okay, and again, that was us finding the minimum, so we changed from negative to positive. Okay, we went from below the x-axis to above the x-axis. Okay, relative minimum is going to be the opposite, and that one is going to be x equals 3. Because this is when we are changing signs from positive to negative versus the minimum was negative to positive. Okay. Part C says intervals where g is concave up. So remember, if g is concave up, that means we are talking about when g double prime is greater than 0, or in other words, when f prime is greater than 0. Okay. Which means the slope on this graph of f is positive. It's greater than 0. What would that interval be? 4 to 6. Okay, 4 to 6. That is right here. That's the only one that is positive. Okay, and positive slope. Okay, part D says the interval where g is concave down, so it's going to be the opposite now. Now we're looking for when f prime is less than 0, so a decreasing slope, and that would be where? 2 to 4, so this side. Okay, and I'm trying to color code as we go to make it easier when you refer back to the notes. Okay. Part E says point of inflections of g. So remember, point of inflections, that means we are looking at where g double prime changes signs. Okay. This is equivalent to where f prime changes signs. Okay. Which means this is where f changes direction. Which is going to be at what x value? 4, because where it changes direction. Okay, right here. X equals 4. Okay, again, changes direction. It's going from a negative slope, and then it goes back up to a positive slope. Changes direction. 2, so 2 and 6 can't be 1 because it's not going in the opposite direction. So if it goes from positive, we would expect it to go negative. For those points, it's kind of just staying constant because of the straight line. Okay. So then F says if g of 1 is equal to 5, what is the maximum value of g on the interval from 1 to 5? So first I'm going to look at the interval from 1 to 5. Okay, so I'm looking from here to here. Okay. And if I want to find the maximum value of g, that means I should be looking at where the function, the capital F of x, that derivative, changes signs from positive to negative. So for the maximum value, I should be looking at only the positive or the increasing section of the graph. So notice I have two parts. I have this part right here in that interval, and I have this part right here. Okay. The one at the top, this is positive. This is our increasing. The one at the bottom is going to be what? Negative, our decreasing. So since I want the maximum value, I'm only going to be looking at just this section here, just the section where it's positive. Okay? If it was asking for the minimum value, where would I look at? Good, that negative section. So here, to set this up, I'm going to say 5 plus the integral from 1 to 3. Because notice in that positive area, it's only going from 1 to 3. Right here, 1 to 3. Okay. Of f of t dt. Okay. I can then look at that area, and since it's nice and pretty 1 by 1 squares, I can count that area to be what? Well, I would say 3, right? So it's 1, 2. These look about a half each, so 3. So 2 plus a half, 2 1/2, plus another half, 3. Okay. So I would do 5 plus 3, which gives me 8. So it's saying the maximum value of g on the interval 1 to 5 is going to be 8. Okay. And remember, we're talking about the function of g, which is the integral from a to x of f of t dt. Yes? Because we're starting at g of 1, which g of 1 would be from a to 1. So it's talking about, if we were to redraw this, because remember, this is just the graph of f. Okay, if we were to redraw this to look like the graph of g, we would still have some space over here of how this would look like. Well, since we can't actually calculate that area, that's why they had to give us this value, g of 1 equals 5. So when they give you that, just take that value and add it to your integral. Okay. Any other questions for 1? Okay, number 2 says let g of x equal to the integral of 0 to the function x over 2 plus 5 of f of t dt, where the graph of f is shown to the right. Find the x value where g has a relative maximum. Okay. So we know that a relative maximum, based off our notes on the first one, on the first part, is when our function g, the derivative of it is going to be equal to 0. So when the derivative of that function is equal to 0. Okay, remember, since g is an integral, if we take the derivative of an integral, it ends up canceling out. And instead of writing f of t, where t is our placeholder, we're going to take that upper bound and plug it into t. So really what we have is that g prime of x is equal to f of x over 2 plus 5 times what? Say that one more time. Not dt. So remember when we were talking about this the other day, when we were doing the accumulation function, we said we always have to look to see if the chain rule applies. Times 0.5 or times 1/2. Okay, they're very loud outside. Okay, and then of course we said that that derivative is equal to 0. Okay, well, since we want to find the relative maximum, we know that g prime of x has to be changing signs from positive to negative. So if we look at our graph of f, that means f has to be changing signs from positive to negative. We would be using which x value for our maximum? 3 or 5.4? 3, because we're looking right here. Okay, remember maximum, we're going from positive to negative. Positive, as in this top part is above the x-axis, to negative, this bottom part is below the x-axis. Okay, versus 5 would be the opposite, where we're going from less to minus to plus, changing the signs. So x equals 3. And so we're going to keep that in mind in order to find that relative maximum. So for now, what I'm going to do is I'm going to take this part, this f of x over 2 plus 5 times 1/2. Okay, set that equal to 0, which means I would have to divide both sides by what to get the function by itself? By 1/2, which means what happens to the 1/2? It cancels out. So then we have the function of x over 2 plus 5 is equal to 0. Well, we know that on our graph, in order for us to have a relative maximum, this has to be equal to, and by this I mean this inside part of the function here, has to be equal to 3. So I'm going to take that and do x over 2 plus 5 equals 3, and then I'm just going to solve for x. So that's me subtracting 5 over, so x over 2 is equal to negative 2, and then multiplying both sides by 2, and I get x is equal to negative 4. Okay, which means that the x value where g has a relative maximum is at x equals 4. Okay, so not only did we have to use the accumulation function that we learned about yesterday, but we had to connect it with the relative maximum that we see on the graph and set them equal to each other. Which means if they were asking for the relative minimum, we would have set this equal to what? 5.4. 5.4.